I'd like to look at one more example in this section, and we spent a lot of time talking about equations of tangent lines, but I want to revisit another idea, which is identifying places where our curves have horizontal tangent lines and also vertical tangent lines as well, because that's something that we've mentioned here and there just very, very briefly. I just want to talk about it because it's, I think, particularly relevant in this section. So it says determine the points where the curve x plus y squared minus y equals 1 has vertical tangent line. We also want to know where we have a horizontal tangent lines. I know we're talking about tangent lines. We must need the derivative. So I have x plus y squared minus y is equal to 1. I'm going to start by finding the derivative of this function. So the derivative of x, that's just 1. Plus derivative of y squared, that's going to be 2y times dy over dx, minus derivative of y, that is 1 times dy dx, or simply just dy over dx. Derivative of 1 on the other side, that's just 0. So okay, we'll take this equation and solve it for dy over dx really quickly here. Shouldn't be too bad. So 2y dy over dx minus dy over dx is equal to negative 1. Let's factor out dy over dx. So dy over dx, that leaves me with 2y minus 1 is equal to negative 1. And then just divide by 2y minus 1. So dy over dx is equal to negative 1 all over 2y minus 1. So I want to determine where do I have any vertical tangent lines, and I need to determine where I have any horizontal tangent lines. So okay, let's talk about vertical tangent lines first, because that's kind of odd. Remember we said for vertical tangent lines, that was a place where the derivative did not exist, where f prime of x does not exist, or dy dx if we wanted to use that notation like we are here. So think about this. Where does this function right here, or excuse me, where does this relation that I found right here not exist? I see this fraction over here on the right hand side. I'm worried about the denominator, because if I divide by 0, that's undefined. That does not exist. So I'm worried about values that would make my denominator equal to 0. So I'm going to take just my denominator. So I'm going to take 2y minus 1 and set that equal to 0. We can solve for y. So let's see, 2y equals 1 and y equals 1/2. Here is my y value, but I also need to find the x value that corresponds to that. So I will have to take that and plug it back into the function that we started with. So let's do that in red here. I've got x plus y squared. We said y was 1/2. So plus 1/2 squared minus 1/2 is equal to 1. So I've got x plus 1/4 minus 1/2 equals 1. Let's see, this is x minus 1/4 is equal to 1. X is equal to 5/4 then, or 1.25 if you're more decimally oriented. So what this means is that we have a vertical tangent, and I can say exactly at what point, at the point 5/4, 1/2. Because that was the y value that made our denominator equal to 0. The other part of this question, it said, hey, where do I have any horizontal tangent lines? What about those guys? Let's do that in green. Where do I have horizontal tangent lines? Remember, that happens when the derivative is just 0. So I'm going to take my derivative that we found right here and set it equal to 0. See if we can come up with any solutions. So dy over dx is equal to negative 1 all over 2y minus 1 is equal to 0. Well, I can't solve with this in the denominator, so we'll multiply both sides by 2y minus 1. 2y minus 1. On the left-hand side, those two cancel. On the right-hand side, 0 times anything is just 0. So I have -1 is equal to 0. Well, that's not the case. -1 is not equal to 0 last time I checked, which means that this is a false statement, which means this equation has no solutions. If this equation has no solutions, what this means for me then is I have no horizontal tangent lines. No horizontal tangent lines. So keep implicit differentiation in the back of your mind. It will be incredibly important for us at the end of this chapter when we start to talk about related rates, which is one of the first really big places where we start to see the practical application and the practical use of calculus. So it turns out that implicit differentiation is going to be really important when we get there.